In this video, we are going to start talking about magnetism. So we have talked about electricity. Should be an S. Let me rewrite that. We've talked about electricity, which is a phenomenon that arises from the presence of charge. Now we're going to talk about magnetism, which we're going to find out is a phenomenon that arises because of the presence of moving charges. So immediately I want us to see that there is a pretty strong connection between electricity and magnetism. That was not always well known. In fact, it was a little surprising when it was found, but we typically don't refer to them as separate phenomena anymore. In fact, you might have heard the word electromagnetic or electromagnetism, which is just a simple combination of electricity and magnetism, because it turns out that these things are kind of two sides of the same coin. So we're going to start developing the language of magnetism, and we're going to do it somewhat by analogy of some things we already know, which is electricity. So let me remind you of some electrical things. If I have a positive charge sitting here and a negative charge sitting here, they will feel an attractive force. We can talk about them in terms of the field that is produced by these charges. We can talk about them in terms of the forces that are being exerted. But we know that this situation will produce an attractive force between the charges. We know that this situation, if I have like charges, will produce a repulsive force. I could just as easily have written negatives here. Two negative charges will repel, two positive charges will repel, and positive and negative charge will attract. Okay, well, let me, instead of writing charges, put the ends of two magnets. And if you've played with magnets before, you might have seen written on them an N and an S. That stands for the North Pole and the South Pole. It's not language that we use a whole lot in physics, but it forms a handy analogy. The word pole just means one of these types. You can call this a pole. This is an electrical pole. This is an electrical pole. In fact, if you remember when we looked at the field for this particular arrangement of a positive and negative charge, we called this an electrical dipole. Di meaning two, pole just meaning one of these particular categories. In magnetism, we don't talk about them in terms of positive and negative. We've named them north and south. If you've ever used a compass, it might be a little obvious why we've called them north and south. But I will say the same thing about these two situations. This and this. Opposite poles will attract. So if I have these two magnets next to each other, close to each other, then I will feel an attractive force between them. If I have like poles, I will feel a repulsive force, right? So in this situation, this feels a force this way, this feels a force that way. In this situation, this feels a force this way, this feels a force this way. Attractive and repulsive, just like I got with electricity. So I want you to focus on the word pole for a second, right? We have this electrical pole and we have this magnetic pole. We call this situation a dipole, but please remember that this situation, where I just have one of them sitting there, is perfectly fine for electricity. An electrical monopole is perfectly acceptable. We're going to see in just a little bit that will not be the case for magnetism, but just to get the vocabulary out of the way, we're going to start referring to these things as poles. We could just as easily call these poles, although we normally don't. We call them charges, but they are poles, for lack of a better term. Okay, now let me remind you what the field of an electrical dipole look like. This is much better than I can draw, so I'm not going to try to draw it, but I have a positive charge and a negative charge, and remember the field lines would connect the two. The field lines are going from positive to negative, and so out here they form these big loops. Inside here they just go straight towards it. We're going to see something really similar. And in fact, when you saw this for the first time, either when I drew it or in your text, or hopefully not right now, but maybe right now, you might have recognized that this looks a little bit similar to something you probably saw in 5th or 6th grade science. when you were talking about magnets. Either your teacher had a magnet and some iron filings, or there was a picture in your textbook, or he showed you a picture, whatever. When you take a bar magnet and you put it under a piece of paper and you sprinkle some iron filings, you get a pattern that looks very much like this. In fact, I have printed one out also. You get a pattern that looks like this, and if I can get these two in frame. What I want you to see is that there are marked similarities between these two. There's a direction to the field. The shape of the field looks very similar. In electricity, the direction of the field goes from positive to negative. In magnetism, it goes from the North Pole to the South Pole. It's reversed in these two pictures, right? This is going this way and this is going this way, but it always goes from positive to negative. In magnetism, it always goes from the North to the South Pole. That is if you are outside of the magnet. The main difference here between these two fields is that there's nothing in between this electrical dipole, but this magnetic dipole, I've got part of the bar magnet in between. And so we're going to have to make a distinction between what's happening inside the magnet and what's happening outside the magnet that we didn't have to make over here. But outside, as long as I stick to that region outside the magnet, really, really similar, right? Same thing with the field. The density of the field lines is going to tell you something about their strength. So as they get closer to the magnet, the field lines get closer together, which means the field is getting stronger. So this has got to be distance dependent, just like this was distance dependent. I've got to be really careful with how I draw the field lines symmetry-wise to show that the distribution of the magnetism, if you will, is uniform, just like it was over here. That is to say, I should expect some symmetry, but really, really, really similar. Inside the magnet, I should point out, things don't go from north to south. They actually go the opposite direction. So if this is north and this is south, let's pick out one of these field lines. Move this over a little bit so you can see. Pick out one of these field lines. Let's say this one. So as they've drawn it, this kind of comes down here, and then it goes out of frame, of course. But we know that this is going to come down and come back up, just like this field line and this field line connects. This field line connects. This field line connects. This one that's coming down is going to connect. I want to pick out one that's coming out of the end. So if I draw the rest of that, that's going to look like this. What we said is this is going to point from north to south. Inside the magnet, however, this continues and actually reconnects with this field line over here. So while in the electrical case, we talked about them starting on, move that over so you can see, starting on positive charges and ending on negative charges. We can kind of say that as long as we're outside the magnet, but we really need to consider the region inside the magnet, and what we can say for magnetic fields is that they form loops. As my teachers said, they bite their own tails. They form loops. That's actually really, really, really important. And this is a byproduct of the fact that I have two poles here, okay? Now, I should point out that when we talked about electricity, we didn't start out with this case. We started out with the field of just one charge, and then we kind of built up to talking about this. So why don't we do that here? In other words, why don't I have just one, one North Pole sitting here, and then talk about the field of a North Pole. You might expect that to look like the field of one charge, where it would go radially outwards and all that good stuff. Well, the problem with that is that this actually, the best we can tell, is not allowed. Does not exist. That is to say, the best we can tell, there is no such thing as a magnetic monopole. There we go. No, I'm having issues today. No such thing as, that's terrible, as a magnetic monopole. That is not the case in electricity. I am free to have one charge sitting out here in space, not feeling the influence of other charges because they're so far away. But interestingly enough, the best we can tell, we don't have magnetic monopoles in this universe. I have to say the best we can tell because that's actually not derivable from first principles. What we're saying there is we've never found one. We're pretty sure we're not going to find one, but in the interest of being fair, there are people that are looking. And I would say that the most interesting thing that could happen to physics in any of our lifetimes would be the discovery of a magnetic monopole. The entirety of electromagnetism would have to be rewritten. That we could save some stuff, but there would be a lot of things that would have to be rethought. It would be a terribly interesting prospect. I personally don't think it's going to happen. Most people don't think it's going to happen, but there are some people that are looking, and it would be really exciting if that was found. But the best we can tell, magnetic monopoles don't exist. And so this statement that the magnetic field lines bite their own tail turns out to not be a specific statement about this geometry. It turns out to be a general statement about magnetism in general. Magnetic field lines are going to form closed loops, always. Very, very interesting. Now, I could arrange magnets cleverly such that I get uniform fields. I remember we saw that with electricity. I routinely had electrical fields that look like this because I had a clever arrangement of charges. I can do the exact same thing with magnetism. I can arrange my magnets carefully so that I get this uniform field. But this always exists only in one particular region of space. And outside that region, these fields will start to curve around and connect. It just so happens that I usually construct this to where I get this nice uniform magnetic field where I want it, in the middle of my experiment, if that's what I'm doing. And so we're going to talk about these fields a lot and the effects of these fields. Just keep in mind, in real life, once I get outside of the little region that I'm showing you, these field lines will curve around and reconnect to themselves. All right. Some terminology. The electrical field, we always, and I will draw one of those uniform fields just to be simple. For electrical fields, I'll do this up here: electricity, magnetism. We called the field E, and if we wanted to explicitly state that it was a vector field, we did that. For magnetism, we're going to call the field B. If I want to explicitly state that it is also a vector field, I'm going to do that. Why B, you ask? I actually have no idea. So in grad school, if you go to grad school for physics, you're going to start using H's here. You're going to start using D's for this. Those are slightly different fields, but they're almost the same thing. The best I can tell is that M is clearly not allowed, because we use M for mass and we use M for a couple of other things, and so M is probably not the best choice. So someone settled on B. I don't know why. If you do, please feel free to comment on this video and educate me. I would actually be interested in that. But we're going to use B for the magnetic field. The electrical field has units of newtons per coulomb or volts per meter. Those are equivalent units. The magnetic field has a unit of Tesla, which I named after Nikola Tesla, who is quite an interesting and fascinating character. Mostly we see this in the context of Elon Musk and cars these days, but the units of magnetic field is a Tesla. I should point out that 1 Tesla is a really strong field. So generally we deal with fields that are in milli or micro Tesla or somewhere in between. You might also see the term Gauss. Gauss is another unit for the magnetic field. We typically don't use that in this course, but it is a unit that's out there. But we're going to stick with Teslas in this course. Okay. All right. Now, let's talk a little bit about sources of magnetism. And I'm not saying sources of the magnetic field. That would be the poles, right? Just like the source of an electrical field are charges, the sources of a magnetic field are the north and south poles. I mean, the sources of magnetism, where does it come from? Well, we have what we call natural magnets. And I'm going to put in parentheses ferromagnetism. Ferro, you might recognize ferromagnetism. This word ferro you might recognize if you know a little bit of Latin as having the root for the Latin word of iron. We normally see this in the periodic table where the symbol for iron is Fe. Ferromagnetism. Now, natural magnets, it's a magnet you could pull out of the ground. Not every natural magnet, as far as I know, is made of iron, but many of them are. And it turns out that iron is a really easily magnetizable material. But the point of this very general discussion is that there are magnets that occur in nature, and we can find them and mine them and pull them out of the ground. However, it has been known since the 1800s that electrical currents produce magnetic fields. You might have heard these called electromagnets. So if you've ever seen footage or in person of a big crane in a scrapyard picking up lots of metal pieces and taking them to a crusher or an incinerator, those are electromagnets. If you run electricity through a coil of wire, you produce an electrical field. We're going to find out later that we can make the general statement that all magnetic phenomena arise from the presence of moving charges, and that's what a current is, right? So even natural magnets, we're going to have to somehow say that natural magnetism is as a byproduct of moving charges, and it turns out we have to look at the atomic level to get there. So let's do that now. Let's actually look at what's going on. So if you remember from chemistry classes or wherever you might have seen this, if you have an atom that is made up of a nucleus consisting of protons and neutrons and electrons, and the electrons usually are drawn something like this, where they're orbiting, quote unquote, the nucleus. That turns out to be somewhat incorrect, but it turns out to be a really useful way to think about them. This is called the Bohr model, or sometimes the solar system model of the atom. And it turns out the electrons are a little bit harder to pin down than just saying, well, they're whizzing around the nucleus like the Earth is whizzing around the sun. We can think of it like that. It's like I say, it's a little incorrect, but it's also a little correct. And so what you have is a system of moving charges, right? Well, if we're saying that moving charges produce a magnetic field, it turns out that every atom has associated with it what's called a magnetic moment. A magnetic moment is the magnetic properties of the atom, and just like a magnetic field has a particular direction associated with it, the magnetic moment has a particular direction associated with it. I just kind of drew one in here at random. But if you take a normal piece of material, unmagnetized I should say, and if I just draw the magnetic moments here, I don't actually draw the atoms. In a normal piece of material, you might have a collection of magnetic moments that look like this. That is to say, the atoms are oriented in such a way that the magnetic moments are randomized. And in general, and remember, these are vectors, so the standard vector summation across the entire object turns out to have a magnetic moment of zero, a magnetic field, that is to say, of zero. Why? It's because there's all this little cancellation, right? In the way I've drawn it, maybe this vector is going to cancel with this vector, and this vector is going to cancel at least partially with this vector. And so on the average, you're going to get cancellation. If that bothers you, think about your own body. You have lots and lots and lots of charges within your body. But you're not electrically charged, probably. And I don't know if you've been shuffling your socked feet across a woolen rug in the middle of winter. If you have, you've got some excess charge, but probably you have no excess charge in your body right now. And that's because all the positive and negative charges in your body sum up to give you a net charge of zero. Same thing is going to happen with the magnetism. All the little magnetic moments are going to sum up to give you a total magnetic field of zero. But in some materials, iron being the notable example, if you place that material in an external magnetic field, so I put an external field, take this object, put it in this field, I'm going to start lining up these little magnetic moments. And so the atoms actually shift. Maybe, and they don't line up perfectly. I still am going to have a little bit of variation, but on the average, what I start to develop is a net magnetic field, which maybe you can see, which is just going to be the summation of all these little ones. So I get some cancellation maybe in the horizontal direction as I've drawn it, but I'm going to get a net field as I've drawn it in the upward direction. Now, most materials, once you take them out of the external field, these things will rearrange themselves. So they kind of go all over the place, just like they were. But in iron, notably, some of them remain like this. And so you can magnetize a piece of iron by putting it in an external magnetic field. And your book points out that you can heat it up or even just tap it. What you're doing is you're giving a little bit of impetus to these guys to be able to move to line up with this one. Heating it is especially effective, although you can heat it too far and then you destroy all magnetic effects. But if you heat it up a little bit, these things are able to rearrange themselves pretty easily. They're going to line up like this. You could also just take a really powerful magnet and rub it along a piece of iron in a preferred direction, and you will start to line up the little bitty magnetic fields here. In iron, we call regions magnetic domains, and we say we're lining up the domains, and that's not important to me if you know those words. What's important to me is you know what's happening. So this macroscopic thing that we call magnetism, that we usually see in bar magnets and horseshoe magnets and electromagnets, has microscopic origins, as of course it has to. All electrical phenomenon has microscopic origins. That's the charge on the electrons and protons. Turns out all magnetic phenomenon have microscopic origins. That's the small magnetic moments of the individual atoms. All right, we will talk about forces in the next video.